Hello and welcome back to Network Information Hiding. Today we will cover Chapter 5, Hiding Patterns. Hiding patterns are can be understood like a map to guide you through the jungle of the available hiding techniques, because there are at least 170 different hiding techniques, most likely much more. And we found a way to describe basically all of these hiding techniques using only a few patterns. So what are patterns? Patterns originated in architecture. They are a solution to a recurring problem in a given context. And they are also reusable and described in an abstract way. In 1977, Alexander et al. Introduced these patterns in the book A Pattern Language, Towns, Buildings, Construction that you see on the right side of this slide. And he also presented a so-called pattern language in which he described 253 patterns. To give you just a brief example, let's say the problem would be to minimize artificial light in a building, and the context would be energy saving. And then the pattern needs to provide a solution for the context in this for the problem in this context, and the solution could be to build a window into a building to receive as much sunlight as possible in that room. Architectural patterns are also discussed in informatics and are rooted in software engineering. They are well known also in user interface design. Check, for instance, uipatterns.com, where an example pattern would be the vertical drop-down menu that you see here on the right side. And you always see a problem summary, maybe the example, some usage aspects can also be covered, and some additional aspects. Patterns are a mighty tool. They can even be used to generate user interfaces in a semi-automated manner. Check further the work by Engel et al. And they are also found in information security. Now, a technique can only be a pattern if it occurs multiple times. In general, scientific community agrees on a minimal number of 3 occurrences. However, in information hiding, there is not such an agreement, and sometimes, even if a hiding technique appears only once, if it's new, then it's still a basis for a pattern at least. And if you describe one hiding method for one network protocol, for instance, and you describe this same method for another protocol, then you automatically have another occurrence. So it does not make much sense to wait for 3 occurrences, and we add new hiding patterns even if we have just 1 occurrence, as long as the pattern is new. But I will introduce the hiding patterns later. So pattern collections comprise patterns of a given domain, for instance, architecture, software engineering, user interface design, or in our case, network information hiding. They can be understood as pattern catalogs, where the terminology here is not unified in the literature, and actually it's that the latter is searchable, for instance, by an index of patterns, but in our lecture we will use both terms, pattern collections and pattern catalogs, in the same way. So I make no distinction. It's just written down here so that you heard of it, but this course is not about patterns themselves. It's about using patterns to describe hiding methods. One problematic aspect for such pattern collections is the linkability of patterns between collections that can differ due to non-unified structures in which the patterns are described. So let's say you have 2 pattern collections and they have some overlapping, and now you want to link these patterns overlapping in an overlapping way. So you want to link one pattern of catalog A to another pattern of catalog B to clear up the situation. That's not always easy to do, but if you stick to one collection and have one unified way to describe patterns, then they are easily referenceable. Pattern languages were introduced to solve the problem of pattern collections in a way that you provide a unified description for the patterns, and they also allow to build links and hierarchies between the patterns, and they also allow you to introduce aliases to prevent redundancies, because sometimes some techniques are known under different names, but they belong to the same core idea, which is the same pattern. There is at least the PALML language, PLML, stands for Pattern Language Markup Language, and this is one dominating example of a pattern language. And we will use PALML to describe the patterns that we use for information hiding in a network. How does PALML look like? Well, it's an typically XML-based structure, and however, in our case, we do not use XML in the end. The important part is that you have predefined attributes. For instance, every pattern has an identifier, an alias, problem description, description of the solution, and so on. And of course, a name, context description, some evidence where you can prove that the pattern was used a few times, literature references, and so on. You can also link a pattern to another pattern. Now, what are hiding patterns? Hiding patterns describe the key idea of a hiding technique. They are kept on an abstract, non-detailed level. So we don't go into all the details. We do not describe some very protocol-specific aspects or something like that. We describe a generic idea. And hiding patterns also help cleaning up the terminology because of alias support. So the same idea published under different names can be combined in the same pattern. And they can form a taxonomy because in the end you have a hierarchy of patterns. So you derive one pattern from another. As mentioned, a pattern is a solution to a problem in a given context. And the problem here is that a stealth information transfer must be realized for a given network protocol, which is the context. And the solution is to use some specific hiding technique that is, however, not always network specific, because we describe it in a generic way. And the pattern combines these ideas so that we have a unified description of the hiding idea. Here are some attributes that we actually use. Because we do not use all the attributes defined in PALML 1.1, for our case, a few attributes are enough. We have a pattern idea, we have a name, we have aliases, we can have an illustration and the context. So where can the pattern be applied? How does it work? That's the solution. Some evidence to literature, cases that use it, and of course the references themselves, and if we want some implementational details like code fragments. Right now we have approximately 170 hiding techniques that are known to us in the network, and they hide secret information and some metadata in the end of network traffic. but terminology is inconsistent and reinventions of ideas were common a few years ago at least. And instead of dealing with all these hiding techniques separately, we only need to understand a few hiding patterns. Because if you understand these few hiding patterns, then you already understood the core idea of these 170 hiding techniques. Initially, only 11, later more patterns were found to describe all analyzed hiding techniques published between 1987 and 2013. 109 hiding techniques were covered back then. But now we have more than 20 patterns and 170 hiding techniques. Also, patterns provide better taxonomies due to their several features like links to other patterns, which allow us to introduce child patterns, alias handling, unified attributes, and so forth. Here you can see an overview of the original pattern-based taxonomy that covered 11 patterns. And what we can see here at first sight is that we have two main categories that you already know, because we have timing and we have storage channels. For the timing channels, we have 1, 2, 3, 4 patterns defined, and for the storage channel, well, we have a distinction first. We can either modify non-payload, like the network protocol header or padding, or the payload itself, which would be in the original view, audio, video, or in general, digital media steganography. But if we focus on this part, then we can either modify the structure of the non-payload. For instance, we can increase the packet size, we can modify the sequence of some header elements, something like that. Or we can preserve the structure, for instance, by replacing some random value with some encrypted hidden information, or changing some value, or saving some data in an unused or reserved header bit. Also, some patterns have child patterns, which are special versions of some pattern. This is the current taxonomy as of 2020. It covers 14 timing and 10 storage patterns plus subpatterns. This looks like a lot of work to understand all this, but trust me, I will guide you through this taxonomy, and it will be easy to understand. Just a few words in advance. We further differentiated timing channels into those that are protocol agnostic, i.e. they do not require to understand the protocol in a specific way. So they can use data in a way that is independent of the protocol's functionality, of the network protocol's functionality, while other protocols are protocol aware. For instance, if you want to exploit frame collisions for secret information, then you need to understand how they work and how you can signal a frame collision. And also, entirely new is the modification of payload. We first thought, okay, there is no way to add this because this is digital media steganography, but turns out there are actually two types of patterns that allow us to modify the payload without performing real digital media steganography. For instance, we can simply increase the payload size. We can also just corrupt user data, and then we have some user agnostic methods. But if we work in a user data aware fashion, then we can try to modify the redundancy, for instance, of voice over IP codecs, or we can change values of the user data in a simple way, or modify reserved or unused areas. Well, this does not include things like LSB steganography on some images or something like that. So we do not focus on the media itself that is embedded in the network protocol, because that's digital media steganography. So originally, we published the taxonomy in this paper, and then it got extended in this book chapter and by this paper, and one new pattern was added in the paper by Velinov et al. 2019. That's the value influencing subpattern here, PS11C. And the latest version of the pattern taxonomy plus a description of all patterns is always available on this website, ih-patterns.blogspot.com. If you look at the website, then you can click on pattern collection, and you have the pattern collection here in the latest version, and you can click on the particular pattern, and then you get all the information, at least in a compact format, on this particular pattern. Okay, let's go through all these patterns in a systematic manner. So first of all, we will look at timing channel patterns, in particular on the protocol agnostic ones, which are just 3. So first of all, we have PT1, the interpacket times pattern. Let's look at that. So how does this first pattern work? Well, the covert channel alters the timing between PDUs. PDUs are protocol data units, or simply packets, frames, that's all the same. Sometimes these timings are called interarrival times, sometimes they're called interpacket gaps. And examples would be to alter the timings between Ethernet frames, IP packets. You can do this on every layer. And as you see illustrated here, different timing gaps, G0 and G1, can indicate different hidden symbols. So for instance, if you send a packet with 1 or 2 seconds after another packet, then this simply creates a method for covert signaling. And next pattern is the message sequence timing pattern. Here, hidden data is encoded in the timing of message sequences. So not in a unidirectional flow or something like that, but in sequences of messages. For instance, a sender could send several packets, of which a receiver only acknowledges every end packets. Or one could send commands m times. For instance, an FTP, you could send the no operation NOOP command twice or just once to indicate a hidden message. And here you can also, for instance, have a covert sender and receiver, where the receiver sends dummy packets to the sender, and the sender acknowledges either every packet or just every second packet or just every third packet. And how the acknowledgements are done represents the hidden information. Rate and throughput pattern. So the covert channel, this is also an original pattern from 2015. The covert channel sender alters the data rate of traffic flow from itself or of a third party to the covert channel receiver. For instance, one could exhaust the performance of a switch to affect the throughput of a connection from a third party to a covert channel receiver over time. So what does that mean? A covert channel sender could use the throughput of a switch. If it's not a good switch, then it does not route all the traffic over separate chips. So if between a covert sender and some other node there's a lot of traffic introduced by the covert sender, then the performance of other switch ports might decrease as well. There's research work that shows that this works, and so the covert sender could, by influencing the rate of the traffic that it sends, influence the behavior of the remaining network that could interpret performance degradation as secret data. Another example would be to directly alter the data rate of a legitimate channel between covert channel and receiver. So like we see on the right side, if we send the data rate 1 or 0, then this is interpreted as different covert bits. Okay, So that's all the protocol agnostic methods. Let's look at the protocol aware methods. We have 5 methods there, and we start with the artificial message or packet loss pattern. That's originally forked from a pattern called PDU corruption, but this original pattern was split into 2 different patterns to have a clearer distinction. So the idea is as follows. Here the covert channel sender signals hidden information via artificial loss of a transmitted message. For instance, one could transfer corrupted frames in IEEE 802.11 to cause a message loss, or to have a man in the middle that drops selected packets exchanged between 2 VPN sites to introduce some covert information. Also here, in the example that I draw below, one could just send multiple packets, and then, for instance, the marked one is dropped or not even sent, and that packet loss would indicate the hidden information. Another one is the message ordering pattern. Here the covert channel encodes data using a synthetic PDU order for a given number of PDUs flowing between the sender and the receiver, like we see here in the graphic. So the original packet order is at the bottom line, packet 1, 2, 3, 4, and so forth. And the covert sender sends the packets in a different order. If they are in order, then this is representing another hidden symbol as if they were sent out of order. Some examples are to modify the order of IPsec, authentication header packets, or simply the order of TCP segments. Artificial retransmission pattern is one where the covert sender sends a message at least twice or multiple times to indicate a hidden message. For instance, it's common that DNS requests are sent multiple times because the reply got lost or the packet itself got lost. So a sender could artificially send such a message, a DNS request, twice to indicate some hidden bit. One could also duplicate other frames, or one could simply not acknowledge a received packet to force the sender to retransmit a packet. That is also imaginable. Then there are frame collisions. Frame collisions, one should say artificial frame collisions, because the sender causes artificial frame collisions to signal hidden information, like seen here. Depending on the timing of other network packets, the sender would introduce a frame that collides with an existing frame from another station to signal some hidden information. This works for CSMA CD and also similar mechanisms. Then finally the temperature channel. Here the sender influences a third-party node's CPU temperature, for instance using burst traffic, and this influences the node's clock screw, and the clock screw can then be interpreted by the covert receiver by interacting with the node, as we see here. There's not much work available on this. Initially, this idea was published by Murder and Sander, and can exploit an intermediate node. Now let's switch to the covert storage patterns. Here we have 2 main areas. One is data that is protocol specific and one that is payload specific. Let's first look at the protocol specific ones, especially the structure modifying ones. So we have first the size modulation, where the covert channel modifies the size of a PDU to encode hidden information. You can do this for IP, you can do this for frames, you can do this for every protocol basically that allows a non-static payload size to signal hidden information. For instance, large packet means hidden symbol 1, small packet means hidden symbol 2. Sequence pattern is one where the covert sender alters the sequence of header or PDU elements to encode hidden information. For instance, in this HTTP request here, we can first send user agent and then accept language, or we can first send accept language and then user agent. But this also works for FTP commands or DHCP options in the options part, even for the IP options in the IP header or the IP version 6 extension headers. There are some sub-patterns, namely the position pattern, and where we indicate hidden information using the position of one element, for instance, one specific option in the number of option in the list of options, or where we have in PS2B the number of elements. In other words, how many elements are added. So in HTTP, that could be how many header lines are present. And then we use the number of header lines to indicate the hidden message. Add redundancy is a very basic pattern where the covert channel creates new space within a given header element or within the PDU to hide data in it. So you add more data, you make the packet larger, but you do not count the number of elements. You count the pure adding of data that is not essential plays a role here. For instance, in HTTP 1.0, you do not necessarily need to send the user agent. You could also create a new IP version 6 destination option and embed data in this option. There's also work showing that this is feasible. Or you could manipulate the pointer and length values of IP version 4 record route options to create space for data hiding. Okay, let's look at the structure preserving storage channel patterns, where we again have 3 patterns. The first one is random value. This is a pretty simple pattern. You have some header field with a random or pseudo-random value, and you just overwrite it with your encrypted secret value. Not necessarily encrypted, but it should look somehow random to not look too suspicious. For instance, you could overwrite the IP version 4 identifier field or the initial sequence number of TCP or the DHCP XID field. Value modulation is also a rather basic pattern where you can select one of n values that are valid. And for instance, you could send a frame to one of n available Ethernet addresses in the LAN. So let's say you have a 48-bit network address, a host address, but only n hosts are available in the network. So you select one of the n hosts to signal your hidden information. You could also encode information by the possible TTL values in IP version 4 or in the hop limit of IP version 6, while you should not select unplausible values. For instance, most TTL values are not larger than 128. Another example is shown here with HTTP. So HTTP is not case sensitive, and you could select lower and uppercase characters here to signal hidden information. This is a very simple approach, and also it will raise suspicion, but it works. There are 3 subpatterns. One is the case pattern that we see here for the HTTP request, where we just modify the case of letters in plaintext protocols, for instance, HTTP, POP3, NNTP, SMTP, things like that. Then there's the least significant bit value, where you modify, for instance, the low order bits of the TCP timestamp option or the TTL of IP version 4. And there's the value influencing pattern. This is rather new and was shown to work with the MQTT IoT protocol, where you perform actions that influence some transferred value. I think this pattern will become more important for IoT-based steganography. In the end of the class, I have a chapter on IoT steganography. Then there's reserved unused. This is also a rather basic pattern. So it works as follows. The covert channel encodes hidden data into a reserved or unused header element. Let's say this is your header and you have some unused bits like the reserved bit in IP version 4 or some padding field, and you can put your secret bits into these fields. Yeah, so several protocols have such fields and you can exploit them using this pattern. Okay, finally, we need to focus on the modification of payload, in the sense that we do not really do digital media steganography, but focus on the network, more network-specific methods. As mentioned, they can be user agnostic and user aware, and we have 4 patterns defined here. So why at all isn't this digital media steganography instead of network steganography? Well, we first thought this would not be possible to extend network-based data hiding methods here, but it is possible. And some of these patterns are also close to digital media steganography, but they never really modify the content itself in a way that, for instance, you modify the least significant bit of some image file pixel value or something like that. So we extended this in a paper in 2018, and we first differentiated between user agnostic and user aware methods. So the user agnostic do not take care about the meaning of the transferred data. And here we have payload field size modulation, where we increase specifically the size of the payload field. But this is, of course, derivated from, as you can see here, from the size modulation pattern. So here's an arrow to PS20 from PS1. And there's PS21, user data corruption, where you blindly override the user data. This is this can be done in many different ways, actually. Also by simply retransmitting user data in a blind way. And then there's user data aware as a category. And here we have also 2 patterns. One is modify redundancy, for instance, by transcoding. So you transfer voice over IP data, for instance, and you recompress the data, the audio data, with a different codec, and this way you save some space that you can use to place your hidden data without increasing the packet size. So this works. For instance, there are different methods also available here. And then user data value modulation and reserved unused is more a link to digital media steganography, and is not only specific to network steganography. We also distinguish nowadays between sender and receiver process. This is not always done, but sometimes the sender and receiver process use different patterns, and we speak of timing and storage covert channels only if the receiver and sender use the same pattern. But if it's mixed, then we speak of a hybrid pattern. There's also a tool available, the CCEAP, Covert Channel Educational Analysis Protocol. that can be used to learn the basics of hiding patterns, however, using the old terminology and the old taxonomy. And however, there are exercises plus solutions available. The tool can be downloaded from GitHub. It's open source, and it uses an artificial network protocol where students can exploit this protocol's functionality to in a way that different patterns are represented. We also took a look at the scientific literature to survey how many techniques were published for which pattern, and most patterns use the value modulation pattern and very few the retransmission or random value pattern. Also, the rate pattern and PDU corruption or loss are rather rare. Some final remarks. Is it better to find a new hiding pattern or to improve an existing hiding method that we already know? Well, both is important and both should be done, and both is valuable. However, simply applying an existing method to some other network protocol without presenting a new pattern or an improvement over existing work is less creative. If you just take, for instance, the reserved unused pattern, and you say, okay, in another network protocol, there's also a reserved unused bit, and I now overwrite it, then this is not really worth a scientific paper because it's rather new nor pretty interesting. See Chapter 9 on details of how new hiding methods should be described for a scientific paper and how the process of finding new patterns works.